All right, this is Professor Cooper again. This is the companion R script session to go with the color theory videos that I've already done. So this is video 3 of the color theory series. I'm going to quickly go through some of the examples and just illustrate some of the points. I had talked in video 1 about the Anscombe data set. I'm going to run some code. You have this code available to you. This was the data sets, the set of data points that illustrate the importance of visualizing your data in addition to analyzing them numerically, statistically. You can see here that the four scatter plots are very different. What you can't maybe see quite as easily, but you can sort of visually see it, is that if you were to run a linear model, see I have the smoother here run to set, the method argument is set to linear model here. If you do regression models, just ordinary OLS on any of these, you're going to get an essentially exact copy of the other. So if you just ran regression on the data, you would think that the data points were roughly the same. You might not see, for example, unless you did some error diagnostics or something like this, that in fact we've probably got a curvilinear relationship between x2 and y2, and we've got an outlier strongly influencing the slope in this x4, y4 data set. We've got an outlier that is probably messing with the estimate a little bit here in terms of the slope. And we've got some random noise in the x1, y1. So we've got very different data sets, but you wouldn't really know that. It might not be as easy for you to be able to know that without actually visualizing the scatter first. So that's a good lesson. All right, I'm going to move on to some theory, some color theory. Again, we talked about hue, value, and intensity. Value can also be called lightness, luminosity. Intensity can also be called chroma, depending on what you're looking at. But generally speaking, we talk about it in terms of hue, value, and intensity. I'll talk sometimes about tinting versus shading, meaning darkening or lightening your colors, depending on the situation. Use hex codes or RGB, red, green, blue. And I'm going to draw some color rectangles in R and sort of illustrate some points. I'm just going to do one for now, but you can use this code to do your own because you're going to actually have opportunities for some bonus. Give it just a second. So I drew some rectangles and then I filled them in with some colors, all right? Here's what's going on. Colors interact. And they interact in ways that are sometimes surprising. In this case, it's not going to be too surprising. It's pretty basic. But when you make a conscious choice about what kind of color scale, continuous scale, discrete scale, light values, dark values, intense values, less intense values, those colors are inevitably going to interact a little bit. And you want to make sure you're not mistakenly doing something with the colors that you didn't mean to do. So here is an example. If you stare kind of at the center of these rectangles, with the larger field rectangles behind being a brighter yellow and a fairly bright royal blue, and then having the smaller area rectangles in the middle, are actually, if I told you the same color, you might not believe it if you were staring at it for a minute, because if you stare at it for a minute, they start to separate. they're interacting with the blue and the yellow fields behind them. The one to the left is becoming closer to a brown, and the one to the right is becoming closer to a true yellow, and they just separate more the more you stare at it. This is the interaction of color, right? So this is the story I think I talked about in one of the videos where, you know, if somebody's got a green shirt and it brings out supposedly the green in their eyes, it's actually bringing out the red in their skin, which is bringing out the green in their eyes. There's a sort of sequenced reaction there, right? So you can do lots of weird tricks with this. You can make colors transparent. You can make colors look like, you can make one color look like two. You can make two look like one. You can really do lots of things. And there's a bonus assignment coming over the next week where you get the opportunity to do something like that if you want to. All right, I'm going to talk a little bit about colors and setting your own scales as well. I'm going to use the MT Cars dataset because why not? It's the one I've been using a lot, and I'm just going to keep going with it. I've got a basic scatter plot here, and right now I'm starting with just picking an arbitrary color, and that arbitrary color happens to be red. Okay, so we've got this first unadorned plot that's just a scatter plot, right? It's a weight of cars and their fuel efficiency, their miles per gallon. And I've used an arbitrary color red. It's maybe better than just black, but it's really not adding that much. Unless you've got a theme of using red a bunch in your graphs and you're on like a markdown page or something like that, and that's sort of your style. This doesn't really add anything. It just kind of sits there. You could let color do something instead. You could let color vary by a number of variables. It could be a third variable. It could also be a reinforcement for one of the other variables, although some visualization experts will say you may or may not want to do that. I think sometimes it actually is a benefit. I'm giving you an example here that may or may not be useful, but it illustrates the point. I've fixed the labels here a little bit, and then I've actually mapped a third aesthetic. I've mapped another aesthetic to the variable fuel efficiency. So fuel efficiency has two variables mapped to it now. This could be useful in some cases if you're really trying to drive the point home. It has the effect in this case. I'm actually using a black and a light gray here on a continuous variable to create a scale. What this is actually doing is it kind of forces some perspective, and it makes the cars with better fuel efficiency and lighter in weight become lighter, and the cars that are less fuel efficient and heavier in the darks, closer to black. It's actually somewhat intuitive in this case, I think. It's a subtle trick. It maps to, and I don't mean this in a graphical sense, it maps to the notion of the horizon line, right? Like if you're looking at the horizon and you see mountains off in the distance, those mountains are going to be light. They're going to be lighter in color than they are in real life the farther they are from your eye. They're going to be lighter and either grayer or maybe a little bit bluer than they are as a landscape right in front of you, right? Right in front of you, you see the quote unquote true colors according to your eye. But far away on the horizon line, you're more likely to see the farther away you are, the farther away the distance is for, say, the mountain, the lighter and the bluer and the grayer it becomes. And this sort of mimics that, right? So it actually kind of adds a weird distance thing, which can be useful in certain cases if you're really trying to emphasize the point. Let's see. All right. I'm going to quickly talk about color ramp palette and color ramp. Color ramp palette is a way that you can set up a scale, a continuous scale, and then you can chop it up with, you can use that scale that you made and then pull discrete values out of it for a discrete scale. So you can say, I want to set up a scale that's got blue and purple on the ends, in this case, and green in the middle. I always want you to use hex codes, but in this case, I'm using just blue, green, purple just for illustration. So I can create this, and then this actually creates a function, rcpal. We didn't need, this equals is the same as the left-hand assignment operator, right? So the left arrow. Then it's actually a function now, and so it requires a number here. And so you write the number of breaks that you want from this continuous scale. So if I write rcpal, rc for me, for my name, you can name it whatever you want. You get these 5 values down here that are 5 hex codes, and the one over here is blue, the one over here is purple, the one in the middle is green, and then you've got hex codes that are in between blue, green, and purple, right? You can actually take the function like this and stuff it in a plot. So scale color manual applies to a discrete scale. If you want to make your own discrete scale, like I've factored out cylinders here, I'm making a discrete scale for this particular variable and this aesthetic. But this time I need 3 because I know there are 3 different values of cylinders. All right, so I'm going to run it. And I've done some other things. I've moved the legend around so that you can see it a little bit easier. We have the blue, the green, and the purple. Since there were only 3 colors, they mapped onto the exact 3 colors from the continuous scale. But if there were more colors, if this was a discrete variable that had 5 levels, 5 categories, then we would have seen those values in between blue and green and the value between green and purple as well, right? So there's another one called color ramp, and the only difference is that it returns a red, green, blue value. So if I say I want pure blue, well, it's giving me a fit here. Okay, there we go. Color ramp at the end of the scale. That's why it's 1, because it wants a proportion there. Is giving us 0, 0, 255, which is the RGB version of blue, and then 0 is at the other end of our scale that we create, which is orange, and that takes these integer values for red, green, blue. Let's see. And then we've got, let's say that you know the integer values for the red, green, blue, but you really want the hex code. You can use ggturn, and you can translate hex to RGB or RGB to hex, no problems. So if you have one and you need the other, it's very easy to translate them. I always suggest using hex codes. It just makes life a little bit easier. And it's easy if you just go straight to like colorhexcode.com and find them. Then you can use color ramp palette. I suggest using color ramp palette. If you want to make your own scale and then cut it up into discrete values, or if you're not, then you just do something like this, where I said color gradient n when it's an actual continuous variable. When, see, color up here is a continuous variable, so scale color becomes a gradient, not a manual discrete scale. And then this n is really great because it means I could add any number of colors here that I want. It could be 2, it could be 50, it doesn't matter. I can put as many as I want, and it will fill in the transitions between those colors and produce the scale of color that I want, the gradient of colors that I want. All right, I guess that's it for now.